Have you ever thought about what influences the pitch of a guitar string? Well, if you haven't, now's the time to think about it. And it all comes back to the great idea about energy, conservation of energy, and then tying in waves to it. So let's think about a guitar string, shall we? Here's a picture of a guitar string, and I go, pew! It's going to go through this oscillation up and down. So at one point it's going to be up here, it's going to be down here. And it produces waves. And so it's the vibration of that string which compresses sound, and the sound has a certain frequency to it, and that's the pitch that we hear. Now, if you notice on a guitar, there's lots of different size strings, and then you can actually change the pitch of each string based on where you place your fingers. And so what you're actually doing is changing the length of the string that vibrates, the part of the string that vibrates. So let's look at what sort of influences things that affect the frequency or pitch that you hear for a guitar string. So let's start with energy. What sort of energy is being used in a guitar string? Well, since it's moving, there's kinetic energy. So kinetic energy is 1/2 mv squared. And then, because it's a string, there's this tension to it, there's this elastic energy, or energy of a spring, or energy due to tension. So that equation is 1/2 kx squared. Okay, so there is our information. Now, if you think back to Hooke's law says that Hooke's law says that the force of tension, the actual force that you apply, the force of tension is equal to K, the elastic constant, times X, the distance that it stretches that spring or rope or whatever you're stretching. So I'm going to actually rewrite this equation 1/2 kx squared and write it out as 1/2 kx times x. You'll see why in a second. Now, k times x is tension. So I'm going to look at this right here and say, all right, k times x is tension. So I'm going to replace this kx with the force of tension. Alrighty, sweet. So it's ft. That's a subscript, not a multiplication. Okay, now if you look at this equation here, there's a 1/2 on this side, a 1/2 on this side, so those cancel out. They're gone, so there's no longer 1/2. So mv squared equals ft times x. Now we're going to try to simplify this a little bit more. If you think about frequency and wave speed, wave velocity, and wavelength, those are all about harmonics. There's an equation that deals with speed, frequency, and wavelength. And that equation is v equals wavelength, this is for wavelength, times frequency. So what I'm going to do is I'm going to substitute in lambda, the wavelength, times frequency, in for v. And if I do that, the mass stays there, but now the v squared is becoming wavelength squared times frequency squared. All right, we're getting somewhere now. Okay, so I used Hooke's law, I used wavelength times frequency as velocity, or speed. Now, let's look at is there a way to simplify this even more? And the answer is yes, we can. Because if you think about wavelength, that's just a length, how long the wave is. So just keep things simple, keep things generic. I'm just going to replace this wavelength with a generic L. So just any type of length. And then this x is also a length. It's the length that you're stretching it. It could be a different length, so there's a conversion factor here, but it's also a length. So now what does that mean? It means that there's an L on this side and L squared on this side, so one of those L's cancels out. So I'll erase that L, and this square goes away. Okay, so now here's what we have. We have mass times length times frequency squared equals tension. I'm going to rearrange this to solve for frequency. So give me a frequency here. So I have to divide both sides by m and L. So we have tension over mass and length. And really, this is equal to frequency squared. So I can square root both sides. But now, here's a good generic equation. Now this is not equals to, because there's some conversion factors that we went through. So I'm going to replace this with approximately or proportional to. It's proportional to. So there's a conversion factor out in front here. We could call that conversion factor C or K or whatever it is. A, some multiplication factor out in front, some number. But here's what happens. If I want to get a higher frequency, let's look at this equation. A higher frequency for a guitar string. It all deals with energy and waves. So let's look at what I can change. If I increase the force of tension, if I make those strings tighter on the guitar, by increasing the tension goes up, frequency goes up. In fact, it's squared, so it goes up a lot. The mass of the string. The thicker the string is, the heavier it is, the more massive it is. So if I increase the mass of the string, then if mass goes up, since it's in the denominator, the frequency goes down. And that makes sense too. Think about that. The thicker strings are lower pitched. the length of the string. If I have a long string, then it takes longer for it to oscillate back and forth, so it's a less frequency. So the longer the string is, the lower the pitch. So if I put my fingers on one of the ends and make it a shorter string, that's going to increase the pitch. It's going to produce a higher pitch. So I can change the pitch of a guitar string or any stringed instrument by doing three things. Okay. Increase the tension, decrease the tension, that's going to change the pitch. Have a bigger, thicker string or a skinnier string, that's going to change the pitch. Or where I place my fingers changes the length of the string, which also changes the pitch. So that's why you got those guitar rock stars that can do amazing things, because they understand how those three factors can influence the pitch that we hear as sound. So hopefully that makes sense. And hopefully we now understand that, hey, energy is important, waves are important, and everything's connected to make some beautiful harmonic music. Woo! Yeah. Have a good day.